Hello, everyone, and welcome to Sustainable Horizons webinar series. My name is Pooja Rao, and I'll be facilitating today's webinar along with Wendy, Sarah, and Colleen. But before we start, I have a few announcements to make regarding the duration and structure of the webinar. So the webinar is about an hour long, and we welcome questions from our participants during and after the webinar. You can either put your questions in the chat or you can even ask them by turning on your microphone. If you do put your questions in the chat, that at various times during the talk, I'll ask the speaker these questions on your behalf. Additionally, our speaker is also available for about 10-15 minutes after the webinar. So if we have questions that we cannot cover during the webinar, we can ask her those questions after the webinar. Also, a recorded version of the webinar will also be available on our YouTube channel. We'll send out more information about this in the follow-up email. Another important thing that we would like to request you is filling out our feedback form. It's a short form. Most of the questions are multiple choice, and it shouldn't take you more than a few minutes. And we would really appreciate if you fill that out because it provides us feedback, which is very important in improving the quality of these webinars. So please do fill them out. For those of you who are just joining, hello and welcome, and we'll be beginning our webinar very shortly. All right, so as you all know, the topic of today's webinar is Introduction to High Performance Computing, and we are very happy to have Ms. Virginia Trueheart as our speaker. She has an extensive background in high performance computing. She's a research engineer in the HPC applications group at TAC, which is Texas Advanced Computing Center. She works with users in providing them technical and non-technical support for troubleshooting issues related to the use of TAC machines. This includes working with HPC researchers to provide internal support around software maintenance and issue tracking. She also takes part in teaching and outreach at TAC, working on developing new training material for users and helping coordinate responses to users. So without any further delay, let's welcome Virginia Trueheart. Go ahead, Virginia.
Yeah, thanks, Pooja. So like she said, I work for Texas Advanced Computing Center. So there'll be a few examples in this presentation as I go over, and all of you from Stampede 2. Most of you should have access to this machine via Exceed. So if you have an Exceed account, you either have access to systems similar to this one, or you have access to Stampede 2 itself. So with that in mind, we'll start with the overview. So what is HPC? For the most part, high-performance computing generally refers to the practice of aggregating computing power in a way that delivers a much higher performance than you could get out of a typical desktop computer. The idea is that you can run something at a very large scale and get higher throughput. So if you have a pretty standard example is in biology, where you have, say, a genome project where you need to run something through a Python code that processes something. And generally, this is a serial code. So it's a single task that needs to be processed repeatedly for different portions of the gene. With a high-performance machine, the idea is that you can then stack multiples of this so that you could run several things at the same time, or you can run what's called parallel computing. So a single job has multiple tasks doing different things, and then everything coheses back together at the end. So again, the idea is highest throughput, lowest latency, so accessing the file system is relatively easy. And generally, high-performance machines will run much faster than your laptop will. Stampede 2 looks something like this. Peak performance is about 18 petaflops. For context, Blue Waters, which was the last large NSF machine, was 13 petaflops. And that's the number of floating point operations per second that can be run. A petaflop amounts to 1,000 million floating point operations per second. So that gives you a general idea of the scale at which this machine is able to process data. We have a few thousand nodes, all of which interconnect on OmniPath Fabric, and we make use of 3 Lustre file systems to help facilitate I/O latency to make sure the file system can keep up with the amount of computing that's going on the compute nodes. Sorry, wrong way. Architecture. So this is more of a visual representation of what a high-performance machine looks like. And so Stampede 2 is made up of 2 different kinds of compute nodes, SKX or Skylake nodes, and KNL or Knights Landing nodes. Both are Intel. Intel nodes have a slightly different architectural makeup, and so run in slightly different patterns. But you log in by SSH to a login node, which is separate from the compute nodes. And to interact with the compute nodes in order to run your job, you use what we refer to as SBatch, or Slurm is a job submission management system. And from either the login nodes or from the compute nodes, you have access to all of the file systems via the OmniPath network. Each node has a variety of cores available. And this is, the way this is divided is that each node on the Skylake system has 48 cores. Each core is capable of handling 2 threads, so you can have up to, basically you can run 2 tasks per core if desired. So that's 96 tasks per node if you want to max out the node. And it has a relatively high clock rate of 2.1 gigahertz. There's also local RAM, so this is memory that is confined to the node of about 192 gigabytes. And you will also have access to the memory storage on the file system. Physically, it looks something like this. The KNLs have a significantly more cores per node, but the clock speed is lower. So the KNL nodes tend to be better for the first kind of job I described, where you have multiple serial tasks that can be run independently but can be run all at once. Whereas the Skylake nodes tend to be better for NPI and parallel programming because the clock speed is higher and it's able to process the interaction between each task at a higher rate. So the high-level concept is, why would I use a rich HPC resource? Depending on what you're working on, your data sets might be huge. You might want to gather some very granular data about what you're researching. You might also be interested in developing visualizations or developing predictive scaling to see what's changing over time with the data that you're collecting. Examples of this internally are that we use these machines to help track the real-time water collection and flood states during the Harvey hurricanes. So in near real time, we were able to tell where the deepest water was in which parts of the cities and help try to coordinate things like emergency response. So the scale of your data can essentially be as large as you would like it to be. But depending on what you're trying to do, there's a variety of models available and ways in which you could use an HPC machine to further develop your research and get higher throughput on all of your calculations. Here's a few things that you can find on a system. Stampede 2 is based on a Lua module system. So you can always access basic compilers and libraries. So we automatically provide you with access to Intel compilers and GNU compilers, as well as all of the requisite libraries for those. We also have modules for a lot of the popular packages, such as Python or LAMMPS or VASP, anything that's relatively common in a variety of fields, we already provide a package for it. We do have some licensed software available, such as MATLAB, but you can also bring in your own software and run it on the machine. These aren't closed ecosystems. You're not bound by what you see on the machine. So you can use pip if you're running things on with Python. You can download things from GitHub or other direct sources. The only thing to keep in mind when you're doing that is that as a user, you will not have root access. So instead of using sudo install commands, you will install things locally, specifically to your account. And this is the sort of thing that if you have issues with, you can always open a ticket and we're happy to help you work through how to get your particular piece of software installed. So after you decide that the work you're needing requires more computing power, then what do you need in order to get on those machines? So most of you already have Exceed allocations, so that gives you a user account. And then you need an allocation and a project on the specific machine, and the two-factor authentication, which is required by all Exceed systems now. And once you have those logins set up, then you're ready to access a machine. When accessing the machines, we use SSH, which is a secure shell protocol. We can come back to some of these more complex options later, such as customizing your environment, but for the most part, we tend to truncate things in a config file to make access a little easier, and we'll get into that a bit later. The important thing to remember about this is that it's a secure network, and it allows you to log into Stampede, which is considered a secure system, over the internet, which is considered an unsecured system. So it does require two-factor authentication, and once you log in with SSH, then you have access to all of the content of the Stampede machine. When you first log into a machine, you're always going to land on what we call a login node. A login node is where you can manage your files, so moving things, copying things, like importing or downloading new files, or exporting files out to local storage. It's also where you're going to build your own software, and it's also where you submit jobs from. The compute nodes, on the other hand, are for actively running your code. So you can run jobs, which you can submit remotely, or you can test your applications through interactive sessions. So you can visually, because we allow interactive access to the compute nodes, you can visually interact with any of the jobs that you are working on. So you can see how things are functioning in real time, and this makes code development easier, and also sort of allows you to debug on the fly. Like if you have specific sections of code that you know are problematic, then you can watch them as they produce output and focus on parts that may not be performing the way you think they ought to be. But from the login nodes is where you will submit longer jobs, or what we call batch jobs, that you submit out to the compute nodes and then you let them run in the background. You don't have to go look at them. The system will keep them in the queue until they can start. And once they start running, then they'll run along in the background and you don't have to do anything to make sure that they get into the system. Allocations. I don't know how many of you have had allocations before or not, so I'm going to cover this, and if anybody has questions about it, we can revisit it. But for the most part, allocations are granted in what we refer to as service units. In the case of all tax systems, our service units are calculated by the number of nodes you request for your job times the number of hours that your job runs, number of hours that your job runs, and the charge rate. And the charge rate is based on which queue you're running in. So as I said earlier, the Stampede 2 is made up of both Skylake nodes and KNL nodes. But on top of that, several of the nodes have different combinations and different queues. So there are development nodes for both SKX and for KNL, and different queues for normal production for KNL and SKX nodes. And for the KNL nodes, there's also different memory management formats and queues that are available. And the charge rate for each of these queues can vary slightly, but for the most part, queues are calculated currently at a level of 1 charge rate per node hour. So in this case, if I were to submit a job that requested 2 nodes and ran for 10 hours in the KNL normal queue, then that would be 20 SUs consumed by the end of the job. The other thing to remember about these allocations is that these are all shared systems. So generally you will be on a larger project, so you're sharing SUs with other colleagues that are also working on projects. And you're also sharing a system with other groups that also have allocations. So it's just sort of a reminder to be a good citizen when you're running jobs. Don't run things on the login nodes. Only request the resources you know you need. And just be aware that it's not like running on your laptop where you have access to all of the resources at all times. The file systems are how we manage data. On a large HPC system like Stampede 2, you run into issues that when accessing files, like accessing stored files, things that are sort of linearly stored become harder to access. So to avoid this problem, we use what's called a Lustre file system. When you're looking at it from a top level, it looks like a single hard disk space. But it is actually combined of several different storage targets and a metadata server lying on top of that. This allows you, either actively or passively, depending on how your code is set up, to stripe particularly large data sets, which involves spreading out files and data across multiple object storage targets. And this allows your code to then reference that data faster because it doesn't have to read down through every piece of data one after the other. It can know which OST to go to first, and it helps sort things faster. So your read times are faster and your write times are faster, and you'll generally see better file performance from a Lustre file system. Each account on Stampede 2 is granted access to the home file system, the work file system, and the scratch file system. Home is limited to 10 gigabytes of storage space. This is because this directory is never purged, and all of the contents of the home directory are backed up once every 24 hours. So if you delete something from your home storage file, we can get that back for you. Work is a full terabyte of storage. Nothing from work is ever deleted, but we don't back it up. So if you delete something from work, we can't retrieve that. Storage space in Scratch is unlimited. You can put as much data there as you need to. However, none of that data is backed up. And if the Scratch file system begins to get too full, we will start removing the oldest and the largest files from the system first. So some of that data is at risk of purge depending on the state of the file system. And that's the other thing to keep in mind, that this, once again, is a shared system. So if someone's job is writing out to a partition on the file system and doing it poorly, it can drag down the rest of the system. So occasionally we will have to cancel jobs and contact users because something in your code isn't running efficiently. And so we'll reach out to you to try and fix that so that the slowdown in the file system doesn't impact other users. This, again, is just the sort of overview I just listed for each of the file systems. It does include the scaling of the number of servers for each file system. So as you can see, Scratch is significantly larger than all the other partitions. So this is a little bit of Unix for people who aren't used to working directly on the command line. When you log into the system, you will land on a compute node, but you will also land in the home directory of the file system. As you move around and change directories using CD, you might forget where you're standing, and so if you type pwd, it will tell you which directory you're sitting in and which partition of the file system you're in. You can also create new directories and move files around. And you can also use any text editors that are native to the command line. So Vim and Nano and Emacs, things like this. And you can install other editors as well if you like. But these are the sorts of things that you can do on the login nodes without impacting other users. But this allows you to stay on the command line and do your work there without having to move a bunch of files from your local machine onto Stampede 2. So there are two different types of codes. Serial code is one of the first ones I talked about. It's a single task that has slightly different input that needs to be repeated over and over and over again. These usually take a single node and a single core, and therefore you can sort of stack things together. And when you start this stacking, you can end up with a parallel code, either in terms of like an array job, or you can start using the MPI programming, which is a message passing interface, which allows each core on the node to manage a different task, but then they can still communicate with each other across cores and across other nodes. So most jobs will use more than a single node, and this allows you to acquire higher throughput. You'll also come across some hybrid codes that use both serial input as well as MPI tasks. So MPI tasks are the most efficient to run on a high-performance computing machine. This involves developing point-to-point communication between processes. So a task on one core can talk to a task on another core. Collective communication implies a synchronization point. So as all of these nodes talk to each other, the idea is that then you can rejoin things at the end of the job to sort of collect your output and redirect it to something that is readable, either for restarting the job or for storing that data for later post-processing. In TAC, we handle this with a wrapper we call IB run. This wraps up the standard MPI run executable that you most commonly see, and it incorporates portions of the TAC environment to make sure that things run properly within our system. It allows you to execute jobs across the entire node. MPI functions allow communication between all cores and all nodes, and generates either point-to-point or collective communication. Here's a little example of point-to-point communication versus collective communication. Point-to-point communication is useful when you have different tasks that need to be executed. All the nodes can communicate, but they don't necessarily have to share all of the same information, and you can sort of discretely define tasks and how much energy to direct to any particular task that you're executing. On the collective side, you can instead use something like MPI broadcast, which will take a single set of information and then spread it out across multiple cores to work on the same problem, and then you can use MPI gather to bring everything back to a single point for output. For the most part, when you run jobs like this on your local machine, you are running them in what we call an interactive style. This means that you can see the job and interact with the job as it is running. This is useful in debugging, but when you're running something on a particularly large scale, it can consume resources you don't necessarily want it to. Additionally, it's much harder to interact with jobs when they are made up of a larger number of nodes. Usually when you're running on your laptop, you're running on a single node. However, if you submit a job using SBatch, this submits the job to a queue, and then the system handles it in the background for you. This allows you to run much larger jobs with more nodes, and you don't have to keep an eye on what the job is doing or how to keep track of it, and you don't have to provide any further input. It can just run in the background and you don't have to worry about it. It also allows you to run multiple jobs simultaneously. If you're running interactively, then you can only handle that, that single job. Most of the queues on Stampede 2 will allow you to submit multiple jobs at once. Depending on the queue, some allow for much higher throughput than others. It's always a good idea to go over the queues before you submit a job and pick the one that most fits your needs. And that comes down to knowing your code and knowing what kind of performance you're looking for. And by picking the queues that are more focused on your particular code, it sort of helps distribute the workload across the system so that no particular queue is being overused for a particular reason. Again, when submitting jobs, you do have to remember that this is a shared resource and there are only so many nodes available. So sometimes the queue wait is a lot longer than running interactively. But once you've put something in the queue, your job will eventually run. And you just don't have to worry about it, and you can set it up where it emails you when the job submits, and it will email you when the job finishes. The most important aspect of this is that you don't run on a login node. So you can submit the job from the login node where you say SBatch and then your job file name. But what you don't want to do is say start Python from the login node. So if you are sitting on a login node and you just type Python, that starts running the Python program on the login node. And this, because the login nodes are shared, this takes up a lot of resources and will slow down other users. So just remember that if you're doing any computation, it needs to be set to a compute node. This is an overview of the queues that are available on the Stampede 2 system. All of these numbers for the number of jobs in the queue vary based on the number of nodes available in the system and the frequency of use in that system. Large queues that have the asterisks are special because they take up a significant portion of the system to run. And if you run poorly on them, it can cause large-scale system problems and will also cost you a lot of SUs. So we always have requirements that users have to meet before we allow them to run in the large queue. As I mentioned before, the KNL nodes have different memory settings that we can adjust for. Cache mode is the fast MCD RAM configuration and has a L3 cache setup. Basically, this means that you have access to a specific partition of the MCD RAM, and we configure most of our KNL nodes this way because it is more efficient for what most users are doing. We do, however, also provide flat quadrant mode. And in this mode, both the DDR4 RAM and the MCD RAM act in a non-uniform memory access setup. So if you see NUMA control or NUMA nodes, this is the sort of setup they're talking about. Generally speaking, you need to understand how you're manipulating memory for your code if you're going to use a flat quadrant queue. When submitting jobs on any tax system, you'll use SBatch. SBatch is based out of Slurm, which is a simple Linux utility for resource management. Basically, this is a workload manager. It handles all of the incoming jobs and distributes nodes based on the requests from the job queue. It helps allocate resources and also will help monitor your jobs. So Slurm, as your job runs in the background, will keep track of things like the state of the node, the state that your job is in, whether it's received any completion or kill signals, and also sort of just generally tracks the health of the workload in the system. This helps us make sure that none of the jobs are causing problems, but also helps us see if any particular jobs are not running efficiently. It also evaluates and manages the pending jobs. So Slurm can take a look at what's running in the queue, what's coming up next, and what's requiring the fewest resources, and sort of backfill any gaps so that we get the most usage out of the system as possible at any given time. When I walked by the monitor earlier today, Stampede 2 was currently sitting at 95% utilization. So that gives you an idea of how efficient this Slurm is at filling up the any gaps that are in the system as new jobs come up and old jobs start leaving the system. Using the scheduler with SBatch gets you off the login nodes, which means that you don't need to worry about interacting with the job in real time. And it also means that you are not impacting any other users. So anytime that you're running a particularly large job, then it means that using SBatch is your best option. It will allow things to run in the background. You can run multiple jobs at once, and you're less likely to run into any issues that way. SBatch comes with a variety of submission options, and these will go into your actual job submission file. So generally speaking, when you use SBatch, you will say SBatch myjob.sh. The myjob.sh file will contain Slurm variables that include the ones that you see here. This is how you indicate what queue you want to use, how many nodes you want to use, how long you want to run for. And it also allows you to generate and direct output and error files so that whatever your job is doing, you can send it to a specific place so that you can check on output for each one and see if any of them are producing errors or having issues. This is also how you will indicate your allocation. So some users have more than one allocation or are part of more than one group, and you need to specify a single allocation from which to subtract SUs when your job runs. So once you submit a job,
They're asking in the login node under project balance for use, blah, there are 6 columns: usage limit, file usage limit, percentage used. My questions are, what is the difference between usage and file usage? So that's his first question.
Sure. Hang on, I'm gonna have to, PowerPoint has frozen on me, so I'm going to have to escape for a minute here. So the difference between file limit and percentage use. So every allocation, when you log in, you're automatically granted 10 gigabytes in home and 1 terabyte in work. And we track how much, how many files you have saved to each partition, as well as the size of those files. So that basically you can use all of that file partition space up to the maximum listed. So if you have the general usage is the gigabytes, so that's the size of the file, so that's 1 terabyte worth of space, whereas the file usage limit is the number of files. And the number of files limit is larger, but there is a limit there because at a certain point, the metadata server can't handle it anymore. So it's a sort of a way to maintain the health of the file system without generating extra problems, if that helps. Okay. Sorry, hang on a minute while I force quit PowerPoint here. Okay, hopefully it won't freeze up on me again. But yeah, let me know if you need further clarification about how the file system usage is distributed. So anyway, when you submit jobs via SBatch, you can't, you're not looking at them interactively, so you might not know exactly what they're doing. And these sorts of Slurm controls are ways to check on your job and see how it's running, and see if it's doing anything that you don't want it to be doing, if you're worried about something in particular. You can also manually cancel a job if you check in on your output file and it's either generating gibberish or it's not generating output. You can use scancel to go in and cancel your job manually so that you're not consuming SUs from your allocation when you have a job that's not doing what you actually want it to do. You can also use these commands to check on the state of the system as a whole. So commands like sinfo will allow you to look at the queues themselves and see if nodes are up or if nodes are in a particular state, allocated or idle or down, these sorts of things. So here's an example of using SQ and scontrol. So if I have jobs running and I do scontrol or sq-u and then my username, it shows me all of the jobs that I have running. In this particular case, I had a single job running on the development queue. And you can see what time the job started and how many nodes I was running on. It also gives me the name of the node that I'm running on. So in this case, I was running on C455-001. This can be useful if something happens to your job while it's running and you're not sure if information you get back is a problem from your code or if it's a problem from the node itself. So if you have the node list available and can provide that, then that makes it easier for us to go back and check the logs for the hardware to see if there were any specific problems. You can also look at the job itself using scontrol. So the job that I was running in the development queue, I looked up with scontrol and said show job and listed that job number. And this provides all the metadata we have about that job. So it tells you the user and the group and the priority of the job, when it started, if it has any dependencies, if there was a time limit set on it, if there were any pauses during the job. So if there's any information that's considered metadata that you would like to know about the job, then scontrol will allow you to see that. You can also go in and do on-node monitoring. So when you submit a job to one of the queues and you're not running interactively, it can be running in the background. But because you are the user who's making use of that specific node, you do have the ability to use the SSH protocols to access it. If you SSH to a node that is actively running one of your jobs, you can then use some on-node monitoring commands. So this first command, cat process CPU info, will tell you all of the hardware information about the node. So we'll tell you what's being used and what exists on the hardware. Top will also tell you which of your processes are consuming the most resources. So if you're running an MPI job, different tasks and different processes will be running on different cores, and top will allow you to see what's consuming the most as your job runs. You can also use free to see how much memory is being used. Memory errors are pretty common when running on a large scale machine because the data processing can suddenly develop an exponential curve. So something that seemed to work fine at 2 or 3 nodes is suddenly blowing the roof off the memory limits when you start running on 10 nodes. So checking your memory output can also be valuable. We have a slightly easier to read output of all of this if you use our in-house Remora tool. This is a tool that you can attach in your job script, so your myjob.sh file. You can attach Remora, and as the job runs, it will generate output files for that job that indicate, that sort of process all of this information that all of these commands could give you. It will show you memory usage and CPU usage, all of your read and write activity. You can sort of see how your job is performing in general on a node. So it's particularly useful if you're working on debugging something or if you're trying to improve the performance of your jobs. Another useful thing about tax systems is that we do employ a module file. This is a Lua-based or LMOD system. This allows you to add, remove, and swap software packages at will. So basically, this allows you to customize your environment in a way that meets the needs of the codes that you run. So if you have, if your project requires that you are almost exclusively running, say, lamps, you can set up your environment using modules so that when you log in, lamps is always already loaded, all of its supporting packages are already available, and you won't have to make any adjustments before each run. You can just set your environment the way you want it to, save that condition with module save, and then use that setup every single time that you log in. Module Spider is particularly useful because this will allow you to search all of the packages that we have available on the system. It's relatively flexible, so if you only know the first few letters of something, you can still look it up. But if you would rather just read the entirety of what's available, you can make use of module avail, and this will give you a full printout of everything that exists on the system that you can load and use. It's also helpful to use Module Spider on a specific package name because it will tell you any dependencies that that package has. So if I say I load a package and it will, if I do Module Spider and then that full package and version name, the first section of the Spider output will say, you need this Intel compiler combined with this IMPI version, and then possibly list something like boost or scale-a-pack or something, anything that is required for that package to run properly. It will be listed there so that you know what other packages you need to go retrieve so that you can run your code properly. So that's sort of the general overview of how to interact with a high-performance system. And I know it's sort of the quick and dirty version. So if anybody has specific questions or needs me to go back over something or get more in-depth on something, then feel free to ask, and I will be happy to answer any of your questions.
Thank you, Virginia. That was a great talk. So I think there is questions about if you can go over file storage system in a little bit more details and maybe discuss the use of Scratch, because there were a couple of questions with regards to that in the chat.
Sure, no problem. So Scratch in particular is our largest file system. It's comprised of 70 servers and has the most space available. The other benefit of Scratch is that it is the most performative. So the read and write speeds of the metadata server on Scratch are much faster than on the other partitions. There aren't any space limitations. You can place as many files or as much data as you would like in Scratch, but it is susceptible to being purged. Purge is not something that we run on any scheduled or regular basis. It's entirely dependent on the state of the file system. So if Scratch fills up, I think our general estimate is somewhere between 90 and 95%, we start gearing up for a purge. And we always target the files that are oldest and largest first. So anything that you've been working on within the past couple of weeks or even the past month generally isn't going to be susceptible to purging. But if you've run a particularly large job and generated a large file, you left a folder on Scratch that's a full terabyte and it's been sitting there for 6 months, that's something that will be purged first. We also don't back up Scratch. So if you delete something or something is caught up in the purge, that can't be recovered. We free that space up so that it can be reused and maintain the health of the file system.
So there is additional questions. So Kevin is asking, what file transfer system do you use? Do you use Globus? And so first question is this, and then there is another question which says, since users don't have sudo access, how can someone make a request for permanent installation of a software that needs to be used repeatedly? So I guess they're asking, is there some way that users can install a software in their own directory?
Sure. So to answer the transfer system first, transfer question first. So Stampede 2 supports Globus between other Xseed systems. So you can use Globus if you're moving files between Stampede 2 and Ranch, or Stampede 2 and Comet, or anything that's on the Xseed system. Globus will work between those. For all other applications, we recommend, or all other sources, we recommend that you use SCP or rsync. If you're pulling something down offline, wget and curl will also work. But if you're, say, moving files from your local machine to Stampede 2, you'll want to use SCP for that.
Okay.
For permanent software installation, what we recommend is that you use Work to install any software that you need. So I have an entire folder in my Work directory that's dedicated to software installations that are just for my account. And once I download and install everything to that folder, I can then add that file path to my path variable. So in Bash, like in Shell, you'll frequently see this $ path variable. You can just do echo $path on your machine and it should give you a path. And what the path does is look for it's where it finds all the libraries and all of the software that's in line that you want to access. So by adding the software installation that's in my work directory to my path, it means that anywhere I install something on in Work, I can then move between compute nodes and file system directories and always be able to access that particular piece of software. So it means that I don't have to have sudo access, but my environment will always recognize that software.
Okay, thanks. So there is another question about file transfer, and someone's asking, how about using grid FTP for file transferring?
Grid FTP. I think grid FTP will function. So you can use something like, if you prefer like a GUI interface, you can set up something like FileZilla that will allow you to sort of see these sorts of things and transfer things over. For the most part, the reason that we focus on SCP and rsync is because they communicate most easily with the two-factor authentication that you have to pass through when you upload files. FileZilla can handle it, but you need to go in and change the settings on the GUI box so that it can generate the pop-up to allow you to put in your two-factor authentication codes so that you can then transfer the files over. So that's mainly why we focus on SCP and rsync, because they're reliable and they handle the login protocols for our systems the easiest. I also see a question about moving between different directories, and I will stop that share and I can bring up a terminal shell to show you a little bit of how to move around inside the system. So logging in is going to be an SSH protocol. And in this case, I will, so on your local machine, which here is this, this is my local IP address. But if you go into your .ssh file, you may or may not have a config file. You can just create one if you want. And here you can see that I have different host names set up. And this allows me to SSH in with a little less work. So I will log in to Stampede2 using my alias. And then my token code. Okay, so now I'm logged in. And here you can see when you first log in, there's your project balances. So in this case, you can see that I am part of 2 different allocations, this SDS 335 and then the A-CCSC. And then you can also see your file system usage. So, and again, usage is the size of the files, and the file usage is the number of files. And so when you land, I land on the staff node since I work for TAC. You'll land on either login 1, login 2, login 3. When you log in, you'll immediately be placed on the home, like in the home directory. To move between, you can do CD $work. And the reason I use the shortcut there is you can see that the shortcut on Stampede2 sends me to the work directory, but then my specific work directory, and then Stampede2. And the reason for that is that the file system exists on each system. So work is universal to every system that we run. So if I do the file system work is internally known as Stockyard. And so if I do PWD here, you can see that I'm 1 level up. So if you have files that you want accessible on any TAC machine, you can put them 1 level up and it's a lot easier to get to them. But here you can see Stampede2, Hikari is another machine we run, Lone Star, Wrangler. So this is sort of the way we help divide things. So I generally recommend moving around using the variables that batch provides. You can do the same thing for Scratch. So CD $Scratch, and that will place you into your specific Scratch directory.
Thank you. So someone's asking that if you don't have a good estimate of like how long your job will take to run, what should you do in that scenario?
So a good idea is to pick a small version of your job first. So an example that runs on your laptop in a, it might run on your laptop in say 3 or 4 hours. And so then you can take that piece of code and submit it and run it on a queue and request the full 3 to 4 hours that it usually takes on your machine, but then see if it actually takes the full 3 to 4 hours to run, or if it completes and finishes before then. And so this gives you a data point on the scale of your job and how quickly it runs on a high performance system. So then if you then increase your job a little bit and then keep the 3 to 4 hour runtime, you can then start to develop the scale at which your job sort of increases. So there's a little bit of trial and error there, but that's because it's highly dependent on each particular code and how much input data it has and how much writing it needs to do. So it's always a good idea to start small and run sort of test points before you just dump a large job on the system and request a full 48 hours and just let it run the whole time and not knowing whether or not it's doing what you want it to do.
Right. And I think I would like to add, like, if you anticipate producing a large amount of data, then have your code print out the restart files. So
Yes.
even if your job quits in between, you can always use it you don't have to start over again.
Yeah, having a restart file, and sometimes you'll also hear us call this a checkpoint, like a job checkpoint, is always always your safest option. Either to, because then you have a new starting point, whether or not the job completes properly, or whether or not it crashes, or whether or not something else happens to it. It allows you to run even larger jobs sort of by combining other jobs. So checkpointing your code is very valuable.
Okay. So someone is asking if you have a demo available for maybe creating a job, like if you have a script that you could submit to show how to request a job.
There's a slide set that I sent to Pooja that she'll be able to share that has sort of walkthroughs on this. Mm-hmm. But here in my home directory, you can see I have a few things here. So I have this rank.py file. So this is a small snippet of code that's an MPI job that uses Python. It talks to each of the processors and sort of provides printout from them. So this is the code portion. So this is a Python file that exists, this rank.py file. Then I created a job file called rankrun.sh. And this is the job file, or the SBatch file. And this is the format that you'll see. And we have other examples of this available in the user guide as well. But you see the SBatch options that I put in. Is the job is named rankrun, and the output file is rankrun.o, and the present.j attaches the job ID to that file name. It's going to run on 20 nodes and only use 8 cores on each node. Run in the normal queue for 10 hours and 10 minutes. Like, this is all very random and not necessarily the best option. So if I edit this file I use Vim as my inline editor. But since this is something small, I will come in here and do normal Q, 60, I want it for 10 minutes, and then save that file. And again, as you can see in here, so that, whoop, sorry. There we go. So here you see, here's the executable line in my job submission file. So this job submission file says Python, rank pi, inside of it. And actually, because this is a multi-node version, I need to put ID run in front of this because I need it to talk to every core on the node. And so then to submit this job, I will do sbatch rank run.sh. And this will start generating an output saying that you're accessing a compute node. It will check all the parameters that are required to run. And then once it submits, it will give you a job ID. And so now I can do what I said earlier about using SQ to sort of check on my job. And you can see that this job is there. It's named what I named it. It's in the state of R. This indicates that it's running. And if I do ls again, you can see that it's generating this output file. So if I go look at this file, you can see the output. And say it's 6 of 60 because I requested 60 cores on one node. But you can see that it's talking to each core of the 60 that I requested. And then the job completed and exited. So now that the job is complete, if I do SQ again, it shows no jobs running under my, it won't show any jobs because I don't have any jobs waiting in the queue and I don't have any jobs running. So that's sort of the, quick version of how do I submit a job. You'll need to create your code file, you'll need to create the SBatch file, and then you will submit the SBatch file using SBatch.
Okay. So someone's asking about availability of MATLAB on the system. So let me generalize this a little bit. So if we need like some commonly used softwares or libraries, how do we see if they're available on the system and how do we load them in the environment? If you can show a demo.
Sure. So to see, if you want to see everything, you can do module avail, and this will print out a very large list of stuff. And if you don't want to read through all of that, you can use module spider. And so since the question was about MATLAB, we will search for MATLAB using module spider. And here it'll say, okay, there's MATLAB and there's, this exists, this module exists, there's different versions of available. And if I want a detailed description, I can use module spider on the specific version. So I can do that here. So MATLAB can be loaded directly, but you do have to have a license to use it. We can provide you with a license, but you have to contact us and let us know the name of your institution and the department that you're working in. And you also need to confirm for us that you will be using it strictly for academic and non-commercial purposes. So under our agreement with MATLAB, these are the specifications that we have to have users agree to in order to grant them access to using MATLAB. But then, once you have that access, you can do module load MATLAB. And now when I do module, we'll do unload first so I can show you. Okay, so if I do module list, you can see these are all the currently loaded modules that I have. This is my basic saved module set. And if I do module load MATLAB, and do module list again, you can see that MATLAB has been added to the modules that are available to me now. And this means that if I open an interactive session using iDev, this may take a second. So this is what I mean by not running on the login node. Like to demonstrate this, I am using an interactive session to go onto a compute node, and you can tell you're on a compute node because it will tell you what node you're sitting on here. But now I can do MATLAB and it will start processing. Although I can't remember if I have my license currently set or not, so this may actually stall out on me. Yeah, and I didn't log in with a -X session. Have access to the license, you can go onto a compute node and run MATLAB. You can also do it in a, you can also do it in a batch job. If I can get this to cancel. So like this is how you would run it interactively. But to run it in a batch job where you would, say you need to run something in parallel, we'll go back to this job file. And so in that case, you would, instead of saying Python rank pi, it would be all of this you would change to MATLAB and then the MATLAB input file that you want to use. And then you could submit that remotely with SBatch. You wouldn't need to run interactively. Let's see, other questions. Regarding the question about, there's one question here about if you have your own software that you want to load, but it requires a dongle. I don't know. We have a thing called Singularity set up that sort of helps accommodate packages that have sort of outside requirements, but I'm not entirely sure about ones that require a dongle. You'd need to submit a ticket on that and we could look into it specifically for you. The other question about MATLAB on maximum cores and allocation, we do have the parallel license for MATLAB, so you can run on all of the cores that are on the node. So if you're on a KNL node, you can run on 68 cores. We have a limited number of seats, but I am not sure what the exact number is at this time. The license is provided by UT, and so I would need to go find the department on campus that manages that. I'm not sure exactly.
Okay, great. I don't think we have any other questions at the moment. So thank you once again, Virginia. That was a great talk, and thanks for demonstrating all those all those examples. Thank you so much. So we'll be staying here for a little bit. We'll let Virginia go, but we'll be here for a little bit. And if I think someone was having trouble logging in, okay. So we can walk through, or if actually if you don't mind staying here for a little bit, can you show them how to log in? Because I think initially someone was having trouble logging in and we were going to help them with
Sure,
that.
we can go through the SSH thing. The last page of this slide is contact information for the portal and email, and for the Sustainable Horizons Institute. So if you need anything, just check the last page of this slide and we'll be happy to help you. But yeah, I'm happy to demonstrate logging in, and I can demonstrate again what I did, where I did a direct login to Stampede, and I can also show you how to log in using the Exceed single sign-on hub option. Okay, so normally, since I'm working at TAC and on a TAC system, I usually log in to Stampede 2 directly. So the first, it's an SSH command, and then it's my username at stampede2.tac.utexas.edu. And then you'll get the prompt for your password, and then the prompt for the TAC token code, because I'm logging in directly. This is not the code you'll need if you're logging in via single sign-on. But that will put you onto the login node. Like here, because I did a long form, it put me directly onto login 3. So you can see that here. If instead I want to use the Exceed approach so that I can access different systems from the same login, I can do SSH-L, sorry, I don't do this one. SSH-L v true exceed dot login.exceed.org. Password. And then the Exceed setup uses either a phone call or a Duo push. And I have Duo set up, so I will put in option 1 and wait for the push notification, and then approve that on my phone. And that brings me to the Exceed login. So that's my home vTrue Exceed SSO hub. If I want to access Stampede 2 from here, I will now do GSI SSH Stampede 2. And here you can again see the output that's generated when I log into Stampede directly. So that tells me now that I'm on the Stampede 2 system. So those are the two options for logging into Stampede.
Perfect, thank you. Thank you so much, and Virginia, thank you everyone. If you have any further questions, you can email us. We'll stick around for about 5-10 more minutes. If anyone has any additional questions and wants to walk through any examples or anything, we can show you that. But once again, thank you everyone.
Appendage, and it points then to Stampede 2. So logging in to Exceed, it's just SSH, this line here. But then once I'm on the single sign-on hub, I can then use GSI SSH to access any of the other Exceed systems. So like this, I think it's, so when I exit out of Stampede 2 from here, it puts me back on the single sign-on hub. And I think if I do GSI SSH list, no. Sorry, I don't use this one very much. There's a way to list all of the Exceed systems that are available. Let me see if I can find the SSH hub. So it's xc-gsi-ssh-hosts. And so when I do that, you can see these are XC. Bridges and Comet and Mason and Stampede and Wrangler are what's available to you.